Hi everybody, today we're going to be doing the 12.07 notes for probability. So we're going to be talking about independent and dependent events. So first we're going to be talking about independent events. So these are events where the outcome of one event does not influence the outcome of the other. So if you have two events, the first event happens, it has no effect on that second event, you know that those are going to be independent events. They are completely separate from each other. Dependent events. This is where the outcome of one event does influence the outcome of another. So that first event does something to change the probability of the second event happening. It has an effect on that second probability. That's how you know that it's dependent, because the first event affects that second event. It is dependent on the first event. Okay, so let's look at some ways to determine whether or not events are independent or dependent. So if we flip a coin for heads and then spin a game spinner for $500, if I flip that coin, it's going to have no effect on spinning that spinner. Flipping a coin does not do anything to change that spinner, so I know these events are independent of one another. Now if I draw a spade from a deck, keep it, and then draw a heart from the deck, that's going to be two dependent events. And the key phrase here is keeping it. Since I pulled that first card from the deck and I kept it, I have changed the total number of cards in the deck. So at first in a deck, there are 52 cards. When I pull that spade and keep it, I now only have 51 cards in the deck when I could go to pull that heart out of the deck. I have changed the denominator. That first event affected the outcome of the second event. So these two things are dependent. And the reason why is because of that phrase, keeping it. Because I decided to keep that first card, I have changed the total number of cards in that deck. If I had replaced the card, there were 52 to begin with, I pulled one out, but then I put it back, there would still be 52 cards in that deck when I go to pull the heart. In that case, it would be independent. But since I'm keeping that first one, it's changing it, they're dependent. Now this next question, it says, how do you determine if two events are independent? Now, we just kind of determined by looking at this last one whether or not events are independent or dependent. A lot of times you can kind of look at it and tell. But what I'm really asking here is, how do you prove if two events are independent? A lot of times you think that you can tell the difference. You read a situation, you're like, oh, those are not going to have any effect on each other. But you're just taking an educated guess. Instead, we want to prove whether or not these events are independent. Because sometimes you'll be surprised that events are actually dependent on each other when you would have thought they were independent. And the way to do that is by looking at our conditional probability formulas. So that formula that we learned last week would be this conditional probability formula here. Probability of A given B equals the probability of A and B on the top, and it's divided by the probability of B. Remember that whatever you're dividing by is whatever you're given. So since I'm given B, I'm dividing by B. That's the formula that we learned last week. Now let's switch events A and B around. Let's now look at the probability of B given A. Remember that the probability of A and B are still going to be on the top. The only thing that's changing is what I'm dividing by. Since now I'm given A, I will be dividing by the probability of A. So that's the only difference from the last formula. Now, in order to determine or to prove if these two events, A and B, are independent, we want to see if these two answers end up equaling each other. If they equal each other, that means it doesn't matter what order you put them in, A given B or B given A, you get the same exact answer. That means that those events had no effect on each other. So if these answers are exactly the same, they're going to be independent. If these two answers end up being different, then you know that they are dependent because something did have an effect on the other. If they're different answers, they're dependent. If they're the same answers, they're independent. So let's go ahead and try some of these problems down here. So I went ahead and filled in my contingency table. You can go ahead and do the same. Make sure that when you're done that you double check that this column adds up to 41 as well as this row adds up to 41. They should always add up to the same number. Okay, so the probability of a female. So there are 18 total females out of our total 41. Easy peasy. The probability that somebody is born in Georgia, that's 12 out of 41. Now this is female given born in Georgia. Okay, so remember from last week there are two ways to do this. I'm going to do the formula way first. So this means that we want the probability of female and born in Georgia on the top. And what do we want to divide by? Whatever's given. We're given born in Georgia, so we want to divide by born in Georgia on the bottom. So what is the probability that someone is female and born in Georgia? Female, born in Georgia, that's 5 people, over the probability that someone is just born in Georgia, that's 12. Now remember, the other way to do this is, since we have a contingency table, we can actually do a shortcut. Our denominator is now just the people born in Georgia. So I can exclude everybody else, and I'm only looking at what is given. I'm given born in Georgia, so I'm only looking at the people born in Georgia. So that means that my denominator is going to be 12. Out of those 12 people born in Georgia, I want to know how many are female. There are 5 that are female, so that's my numerator. So you can do it by using the formula, or you can use it by just thinking about what this means and using the contingency table. So for this next one, since we already did the formula way, I'm going to do it the shortcut way. I want to know the probability of born in Georgia given female. So that given is my new total. So I'm only looking at those 18 females. That 18 is now my denominator. Out of those 18 females, I want to know how many were born in Georgia. So how many were born in Georgia? 5 of those females were born in Georgia. So we want to know, are the events female and born in Georgia independent? Now, you would think off the top of your head that that would have no effect on each other. You might want to go ahead and write down independent. But that's not what I'm looking for here. I want you to prove to me mathematically, is this true? Or are these independent or not? I want you to prove to me with math if that is true or not. And remember, the way to prove that is by comparing those two conditional probabilities. Do A given B, find that answer. Find B given A, find that answer. And then I want you to compare the two to each other. So thankfully for this problem, we have actually already done that. So if I want to find the probability of female and born in Georgia, I want to compare the probability of female given born in Georgia. I want to see if that equals, I'm going to put a question mark on top of this equal sign, the other way around. The probability of born in Georgia given female. I'm comparing those two conditional probability statements. And on C and D, we've actually already done that math. What was the probability of female given born in Georgia? That's what we got for C. That was 5 out of 12. Make sure that is fully reduced. And then probability of born in Georgia given female, that's what we found in D. Make sure that is fully reduced. Do these two things equal each other? 5/12 does not equal 5 out of 18. You're not done yet. So what does that tell you? If these two things do not equal each other, that means these events are dependent. The probabilities change. So these two things do actually have an effect on one another. Whether or not you're female and born in Georgia, those are actually going to affect each other in some statistical way. So since those answers are different, our answer is actually dependent. These events are dependent. Now I know you would have guessed they're probably independent, but through our math we have shown they're actually dependent on one another. Let's try some more examples. So we want to use the definition of independent events to determine whether the events of rolling a number cube, which remember is a 6-sided dice, are independent or dependent. And we want to always prove this mathematically. So the first one, the event odd and the event 3 or 6. So if we're looking at these numbers on a dice, first of all, how many of those are odd numbers? Well, we have 1, 3, and 5. That's 3 numbers out of 6, which reduces to 1/2. Now let's look at B, 3 or a 6. So remember, with or we have to add and then subtract. What's the probability of rolling a 3? There is 1 3 out of 6. Plus, what's the probability of rolling a 6? There is 1 6 out of 6. Minus, how many of those numbers are a 3 and of 6? That is 0. So that is 2 6, which reduces to 1/3. Okay, C and D, given. I want to find the probability that I pick an odd number given that I have a 3 or a 6. Okay, so remember that you can do the probability of odd and 3 or 6 on the top over what's going to go in the denominator, what is given. So the probability of a 3 or a 6. Okay, so let's look at the and first. What's the probability that a number is odd and also a 3 or a 6? How many numbers are odd and a 3 or a 6? So here are my odd numbers. How many of those are also a 3 or a 6? Only this one here. Here's my 3 and my 6. So 3 is the only number that is odd and a 3 or a 6. That is one number that is odd and a 3 or a 6. Over, what is the probability of getting a 3 or a 6? So we just found that in part B, but you could also do it again. That's 2 numbers out of 6. That is 1/3. So there is there are 2 numbers that are a 3 or a 6 here. Now you could do it the longer way with the math, like with actually doing the probabilities. I kind of did a little bit of a shortcut by just using the numbers. And you can use that shortcut that I did. There was one number that was odd and 3 or 6. There are 2 numbers that are a 3 or a 6, and that's going to get you the answer. But what you're really doing is you're dividing those fractions like we did a couple weeks ago. So odd and 3 or 6, that's 1/6. And then we're going to divide that by 3 or 6, which we just found was 1/3. Remember, when you divide fractions, that's keep, change to multiplication, and flip. That's 3/6, which reduces to 1/2. So this is the true math that is happening, but we're just kind of using a shortcut. How many numbers are odd and 3 or 6? That's one number. How many numbers are 3 or 6? That's 2 numbers. Okay, let's look at D. 3 or 6 given odd. So even though we're using the same events, they're in a different order, so we're going to get a different answer most likely, but maybe not. We'll have to see. So given odd is what we're doing on this one. So again, we want the and on the top. 3 or 6 and odd. And this time we're going to be dividing by odd since that is what is given. So that's how your formula changes. You're dividing by what is given. So we still only have that one number that is a 3 or a 6 and also an odd number. only that one number 3. Now we're going to divide it by the probability that we get an odd number. There are 3 numbers here that are odd. So these events are independent or dependent because of what? So when we are determining independent and dependence, where we are looking at these 2 conditional probability statements, these are going to be dependent because the probability of odd given 3 or 6, oops, I'm running into that other problem, sorry guys, does not equal the probability of 3 or 6 given odd. That is why. They do not equal each other, so that is why they are dependent. If they did equal each other, they would be independent. Okay, let's try number 2. The event less than 3 and the event more than 5. Okay, so we want to compare the probability of less than 3 given more than 5. We want to see if that equals the probability of it switched the other way around. Greater than 5 given less than 3. We want to see if these equal each other. So that's an equal sign with a question mark on top of it. Okay, so let's look here. So remember, on the top, we want the probability of less than 3 and greater than 5. So let's look at these numbers. 1, 2, 3, 4, 5, and 6. Let's look and see how many of these are first less than 3. 1, 2, 3. Here's the number 3. So less than 3 is 1 and 2. We do not include the 3 because it didn't say that also 3. Just the numbers are less than 3. We're also looking at the numbers more than 5. That's the second event. And here we go. So remember, your and is on the top. How many numbers are less than 3 and greater than 5? That's 0 numbers. Over greater than 5. How many numbers are greater than 5? 2. We want to see if that equals it, switch the other way around. So here we still have 0 numbers that are greater than 5 and less than 3. On the bottom we have numbers that are less than 3. There are 2. Do these 2 things equal each other? Yes, they do. 0 over 2 is just 0, and that's going to equal 0 over 2, which is just 0. So what does that tell you? These events are independent. Now let's look at the events even and prime number. I'll look at the probability even given prime. And I'm comparing that to the probability of prime given even. Okay, so let's look at some numbers. I'm going to write them down over here. 1, 2, 3, 4, 5, and 6. I'm going to circle all of our even numbers. 2, 4, and 6. And I'm going to box our prime numbers. Remember that 1 is not prime. That's one that people always forget, but it is not prime. 2 is a prime number. 3 is a prime number, 4 is not, 5 is a prime number, and 6 is not. So remember, we put our and on top. How many numbers are even and prime? The only number that we circled and blocked is the number 2, so that's 1 on the top. Over, in this case, we want to put prime on the bottom. How many numbers are prime? We boxed 1, 2, 3 numbers, so 1/3 is on the bottom. Now let's switch gears and do prime, given, even. Remember, prime and even's on the top. So our and is the number 2. Number 2 is the only number that is prime and even, so we have one number that is prime and even. And we divide that by what is given, so we want to divide that by our even numbers. Those are the numbers that we circled. So 2, 4, and 6 are even numbers. That's 3 even numbers. These events do equal each other. These probabilities do equal each other, so these are independent events. So remember, if two conditional probabilities do equal, they are independent. If they don't equal, they are dependent. If you have any questions, reach out to me on Remind or send me an email, and I'll be more than happy to help you. See you next week.